Okay, 1, 2, 3. Okay, good afternoon, everyone. Today we're gonna get into the new system that you have never been say exposed to before. But I have mentioned this a little bit in the beginning of the class that in order to make our structure strong enough to withstand the lateral load, we need a system called frame. Because as far as we are concerned, we have done the floor system and its load transfer. Okay, but you should know that everything we have been doing so far, it's in the two-dimensional world. And when you look at that, the two-dimensional world, you can see it is something like a flat plate. And here we go. Sorry, I think I need to reconnect my pen. Okay, let's hope that it's going to be fine now. Yeah, okay. So what we've been doing so far is the system of flat plate, okay, with beams and everything in it. But when you take the beam, it's the beam system only takes the gravity load, which is the vertical load. So this flat plate is nothing when you see that this flat plate is, say, part of just one floor of the building. And when you have buildings, floor will become just one horizontal flat plate. It doesn't help you to resist the lateral load. Okay. So this floor system needs to form a good partnership with the vertical structure, so that this entire system will work together as a whole to resist the lateral load. And this lateral load can come in the shape and form of wind load or earthquake. So you see, it is very important. And right now, it's a very sad story that some countries, especially the developing country, the third world country, which have always been poor. So they always construct their houses and small buildings without any system like this at all. They just use the wall, and then they put the beam on them. So like that. So this is no system that can resist the lateral load. So when the earthquake hits them, such as Nepal, or the most recent one, Haiti. Haiti is one of the poorest country on this planet. So with the houses built like this, when the earthquake comes, actually earthquake comes through the ground and it shakes the ground so that your building moves like this, back and forth. But a structure like this cannot withstand the lateral force. So most of them collapse. And people, so maybe because the buildings are pretty low rise, so not that many casualties, but some casualties still a lot of people are left homeless. So we need that kind of system, if you know what I mean. So this is the system. See, this is as you can see the raid frame. This raid frame is part of the factory or the warehouse. You need a lot of space down there so that you can keep things. So to obtain a large space underneath, you would like to construct a structure with a long span. So you can see this become a part of the long span structure. And this, because the buildings usually will be closed down around here, correct? So that when this area is closed, it can be hit by the wind. So when the wind blows strong, especially in the Y area, this frame needs to be able to sustain whatever the forces the wind produces. Okay. So this, you can see this is one member, two members now, and then you have another member here. and then another member. So actually, for this case, it's like 4 members are forming a structure that we call frame. And as I showed you before, the special character of the frame is that at this location where the 2 members connect, there must be a joint that we call rigid joint. If you think it is a pin, the frame will not be capable of withstanding the lateral load coming from the wind. So the joint will have to be rigid. And a rigid joint, we will see the definition in a minute. But one thing I can tell you right now is that when the joint is rigid, the moment at the joint, this is my M, moment is not 0. Okay, so that'll be moment there. And this is another example of the frame, you see, kind of beautiful concrete frame to show or to create the sense of the wide area. Usually it is always part of the airport. Okay. All right. So we already mentioned this before. So another one here. You see better in this picture that this is also part of the factory or warehouse. You can see that you have the frame here. Okay. And when you have a part of a wall like this one, you know, the area becomes closed. That means this area can take the wind, right? So when the wind hits the area, this will be the area that will be, you know, responsible by this weight frame. You can see that. So the wind on this blue area, wind can hit this, right? And then this frame must take the wind. So you need a system whereby you can rely on to take the wind for you. So I can, you know, go on and say if it's a second frame like this, so just to help you see better. If we look at this frame, for example, this frame will be responsible for the wind that hits this area, you see? So the wind in this direction. When the wind comes in this direction, let me try to make it clear by erasing this, okay? I'm going to erase this. You know, because when you design stuff like this, you need to be aware of the fact that the wind can also come in this direction. But when the wind comes in this direction, the frame that will help resist the wind load will become this frame. You see? So generally this direction, and of course the area that will take the wind will be this one. Right? But you can see in this direction, when we look far down this, you will have the frame with so many columns and so many beams. So in this direction, things tend to be a lot stronger than in the this direction, perpendicular to it, because in this direction, you have just this one frame to resist the wind. So we engineers tend to analyze this frame more than the one in the longitudinal direction because it's pretty much strong by itself. Okay, but that's the general idea, and you guys know now. Okay, so let's go and try to see when the frame gets complicated, we will need the computer program to help us analyze the structure. Okay, actually there is more than one lateral system to help resist the lateral load. You get a very complicated system in the high-rise buildings such as this one. This is this one, the CS Tower in Chicago. It was a champion for the highest building on planet Earth for quite a few years before it was beaten down by the Taipei 101. Taipei 101 held the record for only a short period of time before it was beaten by I'm not sure which one came before, the Petronas Tower or the Taipei 101, but now they have the, I don't know, it's the Arabian name, the Burj Khalifa, something like that in the Emirates. Okay, anyway, so yeah, that's Taipei 101. So let me tell you a little bit that this building is pretty challenging, because Taiwan, very interesting country, we have some of our alumni going to further their education in Taiwan now, because first of all, it's a very good country. Chinese Taiwan people are generally very nice, very polite. And the education system in Taiwan was laid down by the Japanese during World War II. So the education system of Taiwan is pretty good. And it is very advanced in structural engineering, because Taiwan is an island that is always hit by the storm, and it has earthquake. So it's like the greatest hits of everything, so it has everything. And this building is quite a challenge, because not only that you have to design for typhoon, but you also have to design it for earthquake as well. Okay, good challenge. Anyway, let's skip this. We don't need this. Okay, so this is the first picture. When we need the structure of the frame, we generally need our joint here. This is the joint where members meet to be rigid. If it is a pin connection and the moment there is 0, you may not have the system that is strong enough to withstand the lateral load. Okay, so what is the meaning of the rigid joint? Here it is. You should know that all the joints will remain the same, just like a simplified word. That means if the original angle before the deflection is 90 degrees, for example, it can be, your frame can look like this. It doesn't have to be 90 degrees. But let's say if the original angle is 90 degrees, after your structure has to carry the load, it will have the moment, and therefore the joints will rotate. But the rigid joint will rotate such that the angle would remain the same. So if the original angle is 90 degrees, say, after the rotation, this 90 degree must remain. Meaning, if this member, let's call this member number 2, this member number 3, if member number 2 rotates by 0.1 radian clockwise, member number 3 will also have to rotate by the same amount, 0.1 radian, that is clockwise as well, to maintain the rigidity of the connection. Okay, so which is the second one? The members will rotate about the same degree, and therefore if it is rigid and if it rotates, that means the moment can be transferred from one member to another, and chances are pretty close to 100%. When you have the rigid joint, you will always have moment at the joint. So for those of you who see this and try to analyze, because I've seen it so many times, and then you have bending moment diagram like this to show that this is moment is 0, this is completely wrong. You are no longer deal with a simple beam. This is a system of members now, and moment here generally is not 0. So now you need to start, using your knowledge of the free body diagram to, to the maximum. Okay. So it's very important to know that moment here at joint is not 0. You can think of the rigid joint as, you know, part of the overhanging beam. Okay, because at this point, you have moment at this support, right? Because this is also a rigid joint. So there is always a moment. The main difference between this and this is that this is a rigid joint, but it has a support, so it doesn't move. But this is a rigid joint that is in the air, you know. So when we have the load, it can go, it can move. Creates more problem because there's no way anyone can put the support up in the air like that. Okay. So we are now going to deal with a slightly more complicated system. But if you trust your knowledge of the equilibrium, free body diagram and such, you can just follow those rules all the same, you know? Okay, so let's say this is the stuff that I should not, you know, review for you, but we have done it for the load transfer kind of stuff that, you know, all the support, sorry, supports, right? I shouldn't have to remind you this. Okay. We don't need to talk about this now. Okay. So that is a system of trust in a nutshell. Okay. Let's move on and see what's happening here with the truss. I believe I have it here. Okay. So here's the rigid joint. Let's say we are now focusing. You guys can find this page, I hope. Okay, I'm not going too fast, am I? So let's look at the joint. When we cut the free body diagram of the two members, you see that if I cut the free body diagram, naturally the internal forces are going to show up, right? So if I look at this member, you see, usually now it's if you can be easily confused by the direction, it's time to start focusing very, very seriously. Okay. Now you can see this rate force. Now I should try to draw something alongside this one. Okay. Now let's say I have this member. Okay. When I cut the free body diagram, I can have this, right? You see this force is now perpendicular to the black member. So in fact, this is a shear force, right? When you look at this member, this is a shear, right? Because it is perpendicular to the member. And I can also still have the axial force. And naturally, because this is a rigid member, I can have moment. But to maintain the equilibrium, when I look at the next member that forms the joint, the force in this member would have to be equal and opposite, so that, first of all, my sigma fx is 0. So you can see what is shear force for the vertical member here. The vertical member becomes the axial force for this, let's say, horizontal member. So the shear in, you may be familiar with this as a column, but it's not a column, you know, because it has moment and axial force, right? And the shear. So the vertical force, the red one in here, becomes the axial force in the horizontal member. And the axial force of the vertical member is now going to be the shear for this horizontal member, so that your sigma Fy remains 0. And last one, moment. If this one is clockwise, this one will have to be counterclockwise, so that in the end, your sigma moment becomes 0 as well. So basically, this is a free body diagram. So you have had your knowledge about the free body diagram before in the statics class. It's just the same rules. Nothing ever changes about the rules of equilibrium. in the end, your sigma fx, your sigma fy, and your sigma moment must always be equal to 0. You need to just adhere to those equilibrium equations. Okay, so that is the system of a frame in a nutshell. You may see this picture. So, sorry. Okay, this one, I just expand this free body diagram and include the free body diagram of a joint as well. Some of you may be better off with this free body diagram. You don't need to draw the free body diagram of a joint, but to be able to draw the free body diagram of the joint will help you a great deal when there is the external load applied right at the joint. Because this free body diagram, you know, the one without the joint will not show you how you can handle the load that is applied right at the joint. So this will be useful. You want me to demonstrate this as well? Maybe I should, okay? So I'm just gonna come here and draw the new one because I ran out of space. Okay, so let's look at the frame, okay? Let's say we are going to make this determinant 1. All right, and then I'm going to cut the free body diagram of this and write again. So let's say this member, okay? As usual, after I cut the free body diagram, the internal forces come out right here, and then let's say we have moment here. Okay, now if I am going to include the free body diagram of the joint, I'm going to write the joint. Okay, this is the joint, but you know, over exaggerated. At the joint, at the location where it is connected to this member, let's give it a name, shall we? Let's say this is member AB. Call this AB. So, and then C, of course. So this becomes joint C. Joint B, I'm so sorry. That's joint B. So at the particular location B, you know, to maintain sigma fx equal to 0, now we need to have that equal and opposite. And then the blue one equal and opposite. Okay. Now this is clockwise, so you need the counterclockwise moment here. So this is the end of joint B where it is connected to member AB. Now you see the joint B is also connected to member BC. But looking at the joint itself, you see if at one end it has this, so it has to have this horizontal force to maintain sigma fx equal to 0. And then it has to maintain this sigma fy equal to 0 by having this blue vertical force. And the joint itself must maintain equilibrium in rotation. So it has to have moment, I'm sorry, in this direction. So now if you look at the joint B itself, it is perfectly under equilibrium. So now you have the internal forces on the right side that will be transferred to member BC. Too close. Okay. So when you look at member BC now, you see you need to have this horizontal force equal and opposite. And then the vertical force equal and opposite. And then can go on. And now moment will be equal and opposite as well. So we can easily overlook or not drawing this, because you know when you look at the member A, B, and B, C, this is exactly what I drew here, right? Ta-da! See, it's exactly the same because these two free body diagrams do not include the free body of the joint. You don't have to draw the free body diagram of joint B, but let's say if I have the external load applied here, this external load will be, you know, included in this. So now in balancing sigma fx, you need to include the effect of this purple load, and your two rate horizontal forces may not be equal anymore because of the presence of the purple load. Okay, so that's that. So I can say I'm going to change this color a little bit. If there's a presence of the purple load. Okay, this is the same. This is the same, but this is probably going to be some other colors, maybe that, and therefore this one will be that. All right, but in the end, you know, you just don't kid yourself, or you just don't take things for granted, or you just don't imagine things. You need to include every force and make them under equilibrium, so that your structure, no matter how you cut the free body diagram, must always be under equilibrium. Is there any question, folks? If there isn't any question, I think it's high time that you will be introduced to the first frame. Oh, that's not the first one. That's not the first one. That's the first one. Okay, so let's deal with the one on the left first. Okay, so what do we do first? First thing first is, of course, calculating the reactions, right? So let's begin with this one. Maybe I should use red. You know, I keep things in the simple way first, because first of all, we don't have the frame, this kind of system, or this one. You know, it's just impractical. So the problem with the frames, generally we'll deal with you know, more than 3 reactions. But let's say we go for the basics first. Okay, so in this case, you know that you have the reactions like this. You have one here, you have one here, and this is a roller, so you don't have the horizontal reaction there, you only have it here. And you know by now, because you have 800 kilogram force, I want to include this kind of crazy unit, because it's, you know, it's exactly what we use. It's kilogram force. Why do you have to call it like that? It's simply because kilogram is not force. Kilogram is mass, right? It's a unit of mass. So to say kilogram is force is wrong. But because somehow we, not just Thailand, some other countries as well, we associate the weight with the force. So it becomes sort of, say, reluctantly accepted by the community. Okay, you can call it as a force unit, but you must know it's a kilogram force, not the kilogram as a mass. You guys should have doubts in mind, because yeah, when you had physics class, you know, they always say kilogram is a mass. Okay, but anyway, so that's 800. So you know right away this is 800, right? Correct. So now generally I don't take moment, but For those of you who are not, familiar with, going quickly, you can take moment at this location to obtain that force. But for me, I can easily look at this and say, okay, you see 800 here, 800 there. So that is a couple, right? I have a couple, 800 going like that. And my moment arm is 4 meters, right? So this couple generate moment equal to 3,200 kilogram meter. Can I do this? Anyone? So you can see that the 800, this has to be 800, correct? Because it's the only horizontal reaction you can have. So 800 here and here, but they don't coincide, they pass on to different lines, but parallel. So that's why they themselves will create moment. See, this is the line of action. So that becomes your moment arm, correct? So these two loads will generate moment in the counterclockwise direction equal to 3,200 kilogram meter. So now, in order to balance this frame, I will need the moment equal to 3,200 clockwise, correct? Now I have only these two vertical reactions. To generate the clockwise moments, I would know that this would have to go down and it would have to go up, right? So that you can see that is the clockwise direction of a couple. So now I know that this is the moment, and then the force multiplied by the moment arm, this is now 6 meters. So I can easily calculate that the reaction here is 3,200 divided by 6. See, no need to take moment at all. But for those of you who are not familiar with doing things like this, you can always, let's say, call this point A. You can take moment a day. No harm done. It's just not cool. Okay. So you can do the same. You can take or just sigma MA equal to 0. You will have, and when you take moment a day, you eliminate these two forces. You have 800 multiplied by 4. It's going to be equal to the you call it RD, okay, B, C, and D, RD multiplied by 6. So it's the same thing, right? Just depending on how you look at things, okay? So now we know, let's say, it should be more organized. This is 3,200 over 6. This is 3,200 over 6. And this horizontal force is 800. Okay. So the next step that you should do is to try to complete the free body diagram of each member one by one. Now, keep in mind one thing. If you look at the, I don't have it here. Let's see if I can show you now. Let's try to find it. Not this one. I'm sorry. So, okay. Okay, I'm already in here. OBE description. When we're talking about the frame, let's erase this. Okay, the way I judge your ability is that I would like to see that you be able to calculate reactions. That's naturally, you have to do that first. Okay, if you can calculate all the reactions, you get 20%. So that means if you can get these reactions correct, this one, and that one, including the reaction. That's 20%. Okay. Now, the next step is just to try to obtain proper free body diagram of all the members of the frame. That's another 20%. And that count as your level 1. It's just the basic knowledge of the free body diagram. So let's say if some of you get the free body diagram of member AB correct and then go on to complete the shear force and bending moment diagram of member AB. But then you mess up the free body diagram of member BC. I cannot give the points on shear force and bending moment diagram of member AB at all, because your level of ability is not beyond the construction of the free body diagram. So I can tell you now that when you try to solve the problem, the first thing you should do is just to complete everything step by step. And that is complete the free body diagram of all the members first. And this is not just about the grading your level. This is about the practical purposes of your work as well, because if you can complete the free body diagram of all the members, you should know right away whether or not your equilibrium is correct. If you proceed to do the free body diagram of member AB, and then shear force and moment diagram as well, and then you go on to member BC, and you know something is wrong with member BC, but you don't fix it, it means that you can't actually draw the free body diagram of every member that forms the frame. So for the act of knowledge as a whole, you are not beyond the level of constructing the free body diagram, because you cannot complete the free body diagram of the whole system. Okay, so first thing that you should do is try to complete the free body diagram of everything. So let's look at member AB. Now, I don't even have the solution with me because I kind of like to go like this. Now you know that this, it's too dark. Let's change it. Just the blue one. This is equal to 3200 over 6. Right? So maybe it's fair enough. You can tell right away that this better be 3200 over 6, right? Otherwise, your sigma Fy is bust. So you can make your little note that, you know, by inspection, you know that this one must be equal and opposite to the reaction. And then we have the 800. Correct? Yeah, right, 800. And when you look at this, 800, you will know that by inspection, your sigma Fx will have to be 0. So this has to be 800 as well. You can also note by inspection. You can also further note that this is from sigma Fx equal to 0. And for this as well, come on. Sigma Fy equal to 0. So what's missing? Maybe, you know, I kind of like to draw the support so that I know we are dealing with the hinge here. What are we missing here? The blue forces the axial forces, they coincide, they act on the same line of force. So that's over and done with. But your 800, they do not coincide. So that means without moment, these 800 horizontal forces will cause your member to rotate. And if you can see these two 800s, they're just moving the frame in the counterclockwise direction, right? So that means I, look at this and I know right away that I am going to need to counter this by clockwise movement. Now, let's say, let's not skip it too much. You can take sigma MB equal to 0. That's point B, right? Now you can see that 800, which is this force, 800 multiplied by the height of the frame, that is 4 meters, is equal to 0. Oops, I'm sorry. Is equal to MB. So MB, or you can just say 800 multiplied by 4 plus MB equal to 0, MB is therefore 3200 kilogram meter. So this becomes the complete free body diagram of member AB. So you see, if you don't have this moment, there is no way that member AB will be under equilibrium. We have to have it. Okay, so this completes the free body diagram of member AB. I should try to write somewhere. Member AB. Okay, so is there any question? That should be about the end of the first session. Okay, so I'm just gonna stop the record.